Simple harmonic motion lesson 1 worksheet. So question 1 says a body performs simple harmonic motion when its acceleration is proportional to displacement from a fixed point directed towards that point. What additional conditions, must be satisfied for the oscillations of a pendulum to be simple harmonic? So when we look at the PowerPoint for lesson 1, it lists the different conditions that we need to be true. So I'm just going to put these on the back. So we've got 5 conditions that need to be true. Number 1, the motion must be periodic, oscillatory motion around a central equilibrium point. So in order for something to be simple harmonic motion, it must have this condition first of all. The second condition is that the displacement is a sinusoidal function of time, ranging from 0 to a maximum displacement. The maximum displacement is typically called the amplitude, shown with symbol A typically. So that's condition 2. Condition 3, the velocity is maximum when the displacement is 0. So what we're saying here is, from our little animation, we had a mass that's on a spring. So here's at its maximum displacement. This is our equilibrium position, and that's the maximum displacement in the other direction. So here it's up at the top, the velocity is 0, its displacement is equal to A. Sometime later it's going back through the equilibrium point. Here its velocity is maximum, displacement is 0, and here it's reached the maximum displacement on the other side, minus A. Then it starts going back up, again reaching its maximum velocity as it goes back through the equilibrium point until it's back up at the maximum displacement A on the positive side. So that was condition 3. Condition 4 is the one given in the question. So acceleration is always directed towards the equilibrium point but in the opposite direction and proportional to the displacement. I said those in the wrong way. So it's proportional displacement but in the opposite direction, so this should be down here in my definition. Okay, so what does that mean here? So here we have the object is at the maximum positive displacement. Here I've got a very large acceleration towards downwards. So the velocity is here, is 0 here. It's going to start changing its speed as it moves downwards. Here the acceleration, it's at its maximum, the acceleration is 0. Here it's at the maximum negative displacement, so the acceleration is going to be back up the way. Now, so as it comes down here, its velocity is increasing, it reaches its maximum, so the acceleration is decreasing as it reaches the equilibrium point, and then it starts slowing down as it goes below the equilibrium point to reach the maximum negative amplitude. So the acceleration is in the upwards direction once it passes the equilibrium point, and then it's back to 0 as it goes back to the equilibrium point, and it's going to start pointing back down to the equilibrium point as it goes above it. So the acceleration proportional to the displacement, so the acceleration is greatest at the top or at the bottom, and it's always towards the center. And then we had the fifth condition was the period does not depend on the amplitude. So in the question we were given condition 4, any of the other conditions would be conditions that need to be fulfilled for for simple harmonic motion. Okay, question 2. So question 2, this is, remember, simple harmonic motion, it's periodic oscillatory motion, so the period is always the same. And we've got points A and B haven't been labelled here, but it doesn't really matter. The calculation will just vary depending on what you happen to label it. I'm labelling point A at this side, point B on this side, and we're told the time from A to B is 5.72 seconds. So what we need to think about is how much of the oscillation is it going from point A to point B. So in terms of the displacement, we start at point A, go through the central equilibrium position and get to point B. Okay. Then it's going to go back through the central equilibrium position and back up to point A. That is one full oscillation. So that is equivalent to the period. So here we have half an oscillation because we've gone from A to B, and then we go back from B to A. So if it takes 5.72 seconds to go from here to here, the period is going to be twice that. So the period is equal to 11.44 seconds. Question 3, a body performs simple harmonic oscillations. The graph shows how the acceleration, so it's not the displacement, the acceleration varies with the time. Calculate the frequency of oscillations. So what we have is we have the acceleration, remember, it is proportional to displacement but negative, so this is where the displacement, this value of the displacement at this point, it's at the bottom because the acceleration is going upwards and it's at its maximum. And then we have the acceleration maximally negative here on this side. So this is where the displacement is maximum there, positive, and then we have it back here, negative on this side. So the displacement is doing this. So this is my displacement. Okay, now the frequency of oscillations, and one oscillation is where it goes from the bottom to the top to the bottom again. So that would be one full oscillation. So this is my period. So the time period is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is 13 squares. And 1 square is equal to, well, here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 squares in 1 second, so 1 square is 0.1 seconds. So that gives me that the period of this oscillation is 1.3. The frequency is equal to 1 over the period, so that equals to 0.77 Hertz. Add to the graph above a curve showing how the velocity of the same body varies with time over the same period. So this is where the acceleration has got its maximum positive value. That means it's at the bottom. So it's at the bottom, and at the bottom that means that the velocity is 0. Remember, what we're saying here is the object is down here, it's reached the bottom and it's stopped. So the velocity is 0 at this point. The velocity is also 0 when it reaches the maximum at the top. So that would be at this point, and again at this point. Now, where is the velocity largest? The velocity is largest whenever it's going through the equilibrium position. At this point, it's at the highest amount of velocity. So that's going to be at this point, it will be at its maximum and at this point. So what's happening here? It's at its downwards, so it's going to start moving upwards. The velocity is in the upwards positive direction until it reaches its maximum velocity here. Now it's at the top and it starts going down, so it reaches its maximum negative velocity at this point. Like so. Question 4. A body oscillates with simple harmonic motion on the axis below. Sketch a graph to show how the acceleration of the body varies with its displacement. Right. This is not an acceleration time graph, which would be something like this. Okay. So this is, I'm not expecting a sinusoid here because this is not a graph against time. This is a graph against displacement. So to be able to do this, we need to think about what is the relationship between acceleration and displacement. So looking at our equation sheets, we know that acceleration is equal to minus omega squared x. This is the angular velocity, which is constant. So this is a constant value here. So we can say that acceleration is proportional to minus x. Okay, we've got a directly proportional expression. So if something was directly proportional, that would be a straight line through the origin. That would be for this type of expression, where whatever's on the y-axis is directly proportional to whatever's on the x-axis. Since it's minus the value on the x-axis, that means that whenever the x value is minus, say minus 1, then the y value is going to be positive. When it's a positive value, the y value is a negative value. So the graph we expect looks like this, because the acceleration is proportional to minus the displacement. So that's the type of graph I would expect.